consider that key property of the heap. Parent-child relationship. So we need that description. How to do it in a simple way. We don't want a complicated way, simple way. So without pointer, we can connect parent-child using locations. Because for the elements in array, we only have the location information. So we need to use that location information to do parent-child relationship. All right. So now the binary tree stored in an array, we know an array, the location is in consecutive order. Yep. There is no multi-level structure, right? Yep. Only linear structure. It's a line structure. But we want to describe multi-level structure using linear structure to describe multi-level structure. Here we can do it in this way. Yeah. All right. Yeah. So for each node, we know its index, its location. So we use that information to identify different nodes. So now let's consider relationship between two nodes. All right. So let's just look at the relationship between two indexes. Yeah. We use index to represent that node. So indexes this time. We consider relation between two indexes. So we want to try to find some special way to describe parent-child relationship. Simple way. Yeah, here. Look at this diagram. This diagram. Parent, yeah, that P represents parent node. Then capital L, the left child. Capital R, right child, three nodes. Right? So here, the indices we want to use for parent-child, these three nodes, suppose the parent node has index I, then we only select the node, the element with 2i index for its left child, 2i plus 1 index for its right child. Yeah. In this way, we address the parent-child relationship. Left child just double the parent index. Right child double plus 1. Simple, simple. Yeah. But after, yeah, so after we make this special arrangement, we need to feel if this assumption works well for the whole array. That's important. If this special, arrangement works well for the whole array, we will see it works perfectly for the whole array. Perfect. No problem. Everywhere in the array, we can use this kind of relationship. Yeah. All right. So let's try to understand, what result can we get from this special relationship. Yeah. All right. But there is one little thing we need to be careful. That is the index 0. Index 0 cannot be used when we do this kind of assignment, arrangement. We cannot use the node with index 0. Why? When you double the 0, you still get a 0, right? Then the child, parent, the same node. No, have to be different. Parent, child must be two different nodes. So we do not allow 0 node to be used. So in here, we only one node is not used. Only one. So that's not a big loss, right? Yeah. So we can take it. We can take it. Okay. Yeah. All right. So, all right. So A of 0 is never used. But you can use A of 0 to store some other information. That's fine. Because we never use it as a heap node. It does not belong to heap. Okay. But if you use it to store some other related information, then it's fine. Okay. No problem. All right. Yeah. Now, relationship among heap nodes. Two types of heaps. Now we need to study a heap after this. Now you can see our heap will have the binary structure. Now we need to study the heaps. Two types, max heaps and min heaps. Yeah. Maximum, minimum, max heaps, min heaps. Yeah. So max heaps should have the max heap property. So what's that max heap property? Like this. The value of the parent node, A of I, should be greater or equal to the values of the child nodes. Yeah. That's the max heap property. Okay? Yeah. Then the main heap property, just the opposite. Okay? A of I less than or equal to the values of its child values. Yeah. Straightforward relationship like that. Yeah. Yeah. So sometimes we use the max heaps, sometimes we use the min heaps. So if you want to find the maximum, or if you want to find the minimum, yeah. But these two are equivalent, so we need to study one of the two. That's enough. Okay, yeah. All right, we study the max heap. All right. Now we want to get a visual understanding on a max heap example, what it looks like. Okay, we want to see the view. Yeah. All right. Here, let me give you this. You can see it's a near complete binary tree. Yeah. With 10 nodes. 10 nodes. Inside each circle, I put the values of the array elements. Values. Yeah. So you can see it satisfies the max heap property, right? 16 greater than 14 and 10. It's two child values. Yeah, everywhere you check. Okay, yeah. So you check every triangle. Yeah, those parent, left child, right child, that triangle. 3 values in that triangle. Yeah. If there is no violation, then you can call it a max heap. If there is some violation, you will need to fix it. Yeah. So although it's not a max heap, but we can fix it. Yeah. So we will run some fixing operation to fix it. Okay? Yeah. All right. But that's the binary tree view, but we want to put it in an array. Because that binary tree is only in your imagination. It's not in the, computer memory. It's not in your computer memory. It's in your imagination. But in the computer memory, we have that standard array there. So it's a linear structure. It's a line, linear line structure. Okay, yeah. All right, so now let's put them in that line structure array. Remember, the first location is empty, so we cannot put in the first location with 0 index. Okay, yeah. 16, we put index 1 location. Okay, yeah. Then 2 child nodes, yeah. This relation 14 and 10, 2 child nodes, index 2 and 3, right? Yeah, so our 2i plus 1, okay, all right. Then for element at location 2, then 2 child nodes at location 4 and 5, like that. Okay, yeah. Then the next one, location like that. Next one, you see, no overlapping, right? Package well, okay, no overlapping, not messed up, right? Organized well, right? All locations are used in a perfect way. So with this concrete example, you can see the whole arrangement would work. The heap data structure works well. Yeah. All right, so now let's continue maintaining the heap property. Yeah. Because for the dynamic data, when you put a new element in, you may violate the max heap property. When you add a new element in your current max heap, you may have a violation. So you need to do the maintaining operation to recover its max heap property. So let's look at that details. When the heap property is violated due to some operations, insertion, deletion, etc., how to fix it? Okay. So here we need to fix it. Okay. All right. Here let's talk about the general case. All right. Suppose there is a violation that occurs around this triangle structure. Okay, this local triangle structure. Yeah, it's a local structure. Okay, yeah. All right. So we need to use the swap operation to fix it. Then we can swap the values, okay, to fix it. All right. Yeah. And we assume under that capital L node, there is a valid max heap. Okay. Under that R node, there is another max heap. Yeah. So we only look at this local place. Okay. Local place. Yeah. For other part, we worry later. Okay. Yeah. All right. So local fixing operations. Let's look at the details. And but after you fix this location, then you need to look other places. Check all the places. All right. Yeah. So let's look at the local heapify operation. Local heapify operation. Make it a heapify. Okay. All right. Recursion approach. So you go through different levels by recursion. Recursion operation. All right. If A of I less than A of 2I, that's the violation here, because here we assume max heap property. A of I is supposed to be greater or equal to A of 2I. That's based on the max heap property. So this is a violation. When we detect a violation, then we assign its left child index 2I to largest variable. We use a temporary variable largest to store that left child index. We will use it later. Else, yeah, because else means no violation, right? A of I greater or equal to A of 2I, no violation. Then the parent index I should be in that A of I, should be in that largest variable. Yeah. It means no violation. Okay, all right. But here we only check the left child. We also need to check the violation related to the right child. Okay, so we do another similar check. If A of largest, this time we use the largest value. Okay, current largest value. If A of largest less than A of 2I plus 1, we do not allow it. Okay, so we update the largest value to A of 2I plus 1. Okay, yeah. Otherwise, we do not update the largest. Okay, otherwise we do not do the largest. Then the final step, we need to check if the value stored in the largest variable is different from I. If it is the same as I, then we do not need to do anything, right? Yeah. That means the heap max heap property is followed, nothing to do. So we move to next I. Here we are working on current I. If equals largest equals I, then we should move to the next iteration. Okay, yeah. All right, so assume if largest is not equal to I, that means there is some violation. We need to do swap operation. Okay, how to swap? Swap A of largest with A of I. The A of largest and A of I. The parent. A of largest, it could be the left child, could be the right child. Yeah, but we do a swap with its parent to fix it. Yeah, because for left child, right child, we do not require left child value greater than right child. No. Yeah, the values between left child, right child, either one could be larger. Larger, smaller, doesn't matter. So we only require the parent value should be greater or equal to any of the child values. All right, so here you can see that's the local heapify operation. But you apply it everywhere. You apply this local heapify operation globally. Okay? Globally. Then you fix all the violations. After you apply everywhere, you get a max heap. You get a max heap. Valid max heap. All right. Number 4, heap example, or in order to save time a little bit, first, I give you hints on 3 relatively hard questions. Then if you have other questions, you can prepare to ask me other questions. But I feel most of you may need to get information for these 3 questions. One I feel relatively hard is this question number 13. Look at that. Question number 13. The first one I want to explain. Yeah. Feed the golden ratio. Now, I ask you this question. Is this phi to the 2n plus 1 over phi to the 2n is a positive integer for all positive integer n? This expression for all. It's hard to check all, right? So this one, I designed this question to check your understanding of mathematical induction. Okay. Yeah. If you are familiar with the mathematical induction, then you can answer this question in some perfect way. Otherwise, you can just try your best. Otherwise, so you do some experiments, try the best you can, all right? Yeah, but here I just give you the right way to do it. Although because we need to consider all positive integers. For mathematical induction, you need to consider base cases first, right? So the base cases, you consider 2 base cases, n equals 1 and n equals 2. Then you check, okay? You check. So use some algebra way. Yeah. Here I recommend use the, property, golden ratio property. But if you want to use calculator to plug in, it's fine. So that's one of the options you can take. Yeah. Calculator, plug in, yeah, so you can do that. Approximation, but if it's very close to integer, then you get an idea. Okay, yeah. Another different way, rigorously use the algebra based on the properties of golden ratio. I'll show you in the notes. So that's for the base cases. But other than the base cases, you need to consider the general case. Okay? So yeah. Remember, based on the induction assumption, yeah. Induction assumption, yeah. We assume well, k less than equal to greater equal to 2 less than equal to n, we assume correct. Okay. Yeah, assume correct. Then for k equals n plus 1, we want to show it is also correct. This is the hardest step. Okay, this is hardest step. But there is a special operation I'd like you to look at. Okay. Do this operation. Times okay, all right. Do this multiplication, what do you get? Look at that. With this is identity, right? Because we just do multiplication, algebra. Okay. So that is identity. From this identity, what can you see? What can you see? Can you see anything? Can this identity tell us any special meaning here? That's important. Okay. For example, if I use a special function to represent this expression, if I use g sub 2n, okay, g sub 2n. For that identity, can we say the identity tells us g sub 2n times g sub 2 equals g sub 2n plus 2 plus g sub 2n minus 2? That identity give us this expression. Okay? Yeah. Because this way it looks simpler, right? Then let me write this identity in another clear form, so you can see better. Yeah. Another equivalent form, but you can see things better. So g of 2n plus 2 equals g sub 2n times g sub 2 minus g sub 2n minus 2. Look at this expression. Look at this expression. Okay, yeah. Our goal, we want to see if g sub 2n plus 2 is a positive integer or not. Is an integer or not? Here, let's just see integer. Because from this expression, we can see positive, right? From this expression, it must be positive. For any n, it must be positive. So we only need to show this g sub n 2n plus 2 is an integer. Okay? By induction assumption, you assume when k fall in this range is correct. Can you see the left-hand side is an integer or not by induction assumption, right? This is induction assumption. When k is in this range, it's correct. Okay? Is k in the range? Is k in that range? So integer, integer, integer. You see that? That's the key step. That's the key step. Okay. So, otherwise, if you do not use this trick here, this little trick, otherwise it's not easy to see. Right? How can you see? How can you see? But that identity is critical. First, make sure you understand that identity. It's correct. Second, what's the meaning of that identity? Okay, what's the meaning of that identity? All right, yeah. Then, based on the mathematical induction, you make your conclusion. Mathematical induction. No? All right. It's very powerful. No. So you need to appreciate the power from this question. Yeah. Okay. All right. So this is the first question I want to give you the hint. Then another one I also want to give you a hint. All right. Yeah, this one, number 24. I want to give you a hint. Okay. All right. 6 elements. It is known. This one related to our midterm. There is a midterm question. Okay. Yeah. So this is related to the midterm. One of midterm questions. Okay. Yeah. Midterm. It is known that x1 is not a minimum. Remember, not the minimum. Okay, yeah. Too slow. And x6 not equal to maximum. Okay, yeah. All right. All right. But now let me go refer to that related question in the midterm. In the midterm, remember I asked you that question, given 10 elements, 10, we need to find the one that's not the maximum, not the minimum, right? Remember that question? Yeah. Yeah, midterm, 10 elements. Find one not equal to max, min. Okay, yeah. That question answer 3 comparisons, right? Yep. 3 comparisons. Answer. Yeah. It's pretty smart. 3, you pick arbitrary 3 from the 10. Although we have 10, we just pick any 3 of them. Then we find the median of the 3. Median. Okay. So find the median of 3. Of any 3 elements. That median is greater than some element. It must be greater than the minimum, right? That median is less than another element. It must be less than the maximum, right? Yeah. So this is the best solution we can get, all right? So now you need to connect to that question. But this time slightly different. This time, first, yeah. When we connect to the midterm, this question, this one, our solution should be better or equal to 3, right? At the most 3 comparisons. Yeah, because think about without the given, this is the given condition. Without given condition, we have a 3 comparison solution, right? Yeah. If we do not have the given, the x1 not equal to min, x2 not equal to max, we can use at the most 3 comparisons to get the answer. Yeah. Now we have these 2 pieces of information. We should only do better than 3 comparisons, right? Otherwise, we do not use this information. So your goal, you should, so here there is some good reason you should use 2 comparisons to find the solution. 2. So my question, if it's possible or not, you need to use these 2 pieces of information to help you reduce 1 comparison in our old question. 1 comparison. Yeah. Here, I ask you the question, is it possible? So your answer is yes or no, right? Yeah. If it's no, you just say no. If yes, so here, if yes. Okay. Yeah. If yes, tell me how. Tell me how. How to do it? How to do your 2 comparison? Yeah. But if you tell me how to do it, I will give you 2 bonus points. Okay. If you tell me how, for 2 bonus points. Yeah. But if you only put a yes, and if it's correct, you do not tell me how, you won't get the 2 bonus points. Okay. Because you need to pay some effort. It's not easy. You need to pay some effort to earn that 2 bonus points. Okay. All right. So this is number 24. Number 25. Number 25. Find the median. So I talk about a few times in class. Yeah, but I told you it's pretty hard. It's pretty hard. So here I like to give you some hints to solve. And here, the condition I give you already gave you some instruction. You need to along this direction to solve this question. All right. So here, it is known x1 less than x2 less than x4 and x3 less than x4. Okay. All right. So to solve this question, find the median. Okay. And you need to tell me the details, solution, how to find the median. Okay. Yeah. All right. So here, the basic idea, apply the elimination method. Yeah, it's hard to write things. Yeah. Method. Okay. Yeah. I think that's my memory problem. If my memory is larger, then I can do better. Yeah. All right. Elimination method. So by the given condition, actually we did. Remember, I gave you a few related questions. If you look at homework 1 and the midterm, yeah, especially homework 1, I give you the condition. I ask you which one cannot be the median, right? Yeah. So you connect to that question. Which one? Yeah. Not good. Which one cannot be the median? Yeah, too bad. Yeah. I don't know. How can you make this better? Which one can not be the median? Okay. Then eliminate. After you get that one, eliminate it. Right. It's horrible. Eliminate it. Yeah, hope you can see it. Yeah, yeah, but you write your notes, so you should be fine. Yeah, eliminate it. After elimination, you only have 4 elements. Then you need to update the status. After elimination, only 4 elements. Update the status. What do you mean update the status? Because the old media won't be the new media, right? So you need to update it. Old media in this new 4-element array, what is its rank? Okay, after elimination, you need to update the rank of the media. Update the rank, okay? After you know that rank, this time you use the given information to find that element. You're almost there. Along this direction. Almost there. For example, suppose we eliminated 1 element that is smaller than the median. That's possible. Suppose we find 1. That one is smaller than the median. So we eliminate it. After we eliminate it, then the old median becomes the new second smallest, right? Yeah. Because you eliminate 1 smaller than the median. So the median in the old array, in the new array, it becomes the second smallest, not the third smallest. In the old array, it's third smallest. But you take away 1 smaller one, so it becomes the second smallest. Now, you just find the second smallest element in a 4-element array. We did similar question, right? Remember? Second smallest. We did similar questions. So you know how to do it. Go back to see midterm. You can see in midterm, we had that similar question. Second smallest. But here, remember, you have some given information. You should not waste that. You use the given information. When you find the second smallest, do not waste any comparison. You already have some greater than, less than information. You should use it as much as you can. So then you're almost there. Okay? So with this hint information, you're almost there. But you need to connect dots. Okay? So many places. You know, we have several questions related to this one. In homework 1, midterm, we need to connect. All right, so that's the 3 questions, the hints I'd like to give you. Now you can ask me your other questions you'd like me to explain.
Number 8.
All right, number 8.
Say, is it a good idea to use the median as the pivot?
Right.
Do you mean the position median or the value?
Value median. Our median always means the value median. Yeah. But here, let me give you the information. Yeah. So the value median, you don't know, right? Yeah. In the array, you don't know the value median. So here, in order to find a median, you need to do a lot of comparisons, right? That cost is very high. You know, you need to factor in the cost finding the median. If you need to pay that much cost, do you still feel it's a good idea? That cost is so high finding the median. we know,
So it's like assuming that we don't know it and then we have to find it still.
yes,
Oh,
you need to find it. Otherwise, how can you say certain
this is
element is the median? You don't know, right? That's the point. Okay, you need to find it. Yeah, the median is unknown. We know the median is not given. Nobody gives you the median, right? So you have to find it. If you find it, still a good idea, think about that. Okay? Cost, think about the cost. Find the median. Good question. Yeah.
I have a similar question in
Uh-huh.
vein of number 7.
All right.
After each partitioning step, does that mean every comparison to like our partitioning value? So if we have a partitioning value, we have it at the end of we have it at the end for the array, right? And then we're doing every like comparison to sort our partitions. Is that one step in like the partitioning, or does it mean like the partitioning step as a whole? Like,
As a whole.
okay.
Yeah. As a whole. All right.
Yeah, okay, that makes
Yeah.
sense.
So from beginning to end, also let me bring another point. Also consider our pivot element.
Yeah.
Pivot element belongs to that partitioning step. Pivot. How do you handle the pivot element at the end of the partition step? Yeah. You do it, pivot element. Okay? Yeah. Yeah. Do not forget the pivot element. All right? Yeah. It's important, the pivot element. All right? Yeah. Number 7. Okay. Yeah, 3 order array. Yeah, this one. Okay. Yeah. So 2021. All right, together. Yeah. Because one is for best case, another is for worst case. The formula different. Yeah. Yeah, because other two straightforward. Yeah. So I do not need to, Yeah. Number 20. Yeah. Oh, yeah. 20. Oh, yeah. Still too slow. Yeah. Oh. How to control? Yeah. Oh. Move slowly. All right. Yeah. All right. Together, but one for best case, one for worst case. That tells you the main formula to be used are different for best case because the merge, right? Best case, you use the minimum of n, okay? I'll try my best. Yeah. That is, this one use m plus n minus 1. 2 different formulas for each step. Yeah. The minimum n. Yeah. All right. So here, how do you know you get the best solution? So here I just give you, because you have three subarrays. Can you consider all the possibilities? You do merge, you have a few different ways, right? You have, so so here, A, B, C. Here, let's use A, B, C. Okay. A, B, C, the size. Okay. Yeah. All right. Can you use A, B first, merge A, B, then C? So that is one way, right? Yeah. Another, can you use B, C merge, then plus A? Right? Another way. Can you use A, C merge, then plus B, right? That's the all possibilities, right? Which one is the best? Which one has the minimum number of comparisons? Okay, yeah. Here also three. We also use these three different merge ways, but you just switch to different formula. Each merge you apply is different formula, right? Yeah. So your number should be different. Okay. Yeah. Best case number, worst case number is different. Yeah. So only try three different cases. That's not hard, right? Three, not too much work. Not too much work, right? If I give you 10 summaries, then that's a lot of work. Then nobody can exhaust all the possible cases. Yeah. In that way, I may recommend you the greedy algorithm. Greedy algorithm. We learn if we are given 10 summaries. But I won't give you 10 summaries. Yeah. But you can imagine if the number is too big, you need to use some more efficient method. Okay, but here three, we don't care efficient or not. Only three different cases. Right? Yeah. So these two questions. Okay. Yeah. Good. Any other questions? Yeah. Hope it's not too hard after get some help here, not too hard.
So for 22, are you just basically telling us to
Oh, yes.
disregard?
Right. Yeah, this one. All right. 22. Yeah, actually, this is another big important one. I want to show you how to do it. Yeah. All right. Let me use the remaining about 10 minutes. Let me show you how to do this one. Yeah. Otherwise, most of you won't get it. Okay. All right. So let me consider let me change the number to get a simple case so I can work it out. Now you just use the same method on this question. Okay. All right. All right. Let me change this 21 to 9. Okay. The smaller. The 7 to 3. The 17 to 7. Okay. Yeah. Now let me work it out. All right. Here we have 9 elements. 1, 2, 3, 4, 5, 6, 7, 9. Okay. Yeah. But based on our condition, the given key only in this range between 3 and 7. Okay. So that means we do not need to consider 1, 2, and 9 case. Okay. We only consider the cases in the range. All right. Let's draw the binary tree corresponding to this array. Yeah. So our first comparison is at element 5. So 5 at the root. Yeah. Why I cannot write it? Okay. 5. All right. Yeah. Then 3 after 5, 3 here. This side, 7. Okay. Yeah. Then this 3 left-hand side. Let's say 1, okay? Yeah. 2 here. Yeah, because left-hand side, there are 2 elements. We take the left median, right? So somewhere in the middle with 2 elements. And the left-hand side of 3. So we treat this as left median, right median. So we take the left median.
I guess I figured we were ignoring it. We know the key is within.
Yeah. You can ignore it. Yeah, but if we need to draw, yeah, we draw it like this. Okay. All right. Yeah. But later we will ignore it. Okay. Yeah. 7. So 6 here. 9 there. 9. Oh, sorry. I forgot 8, right? Yeah. I forgot 8. 9. Yeah. So 7. So 6. Then 8 here. And a 9 here. Okay. That's the tree. Now, let's shade those elements that we need to consider. These 5 elements, we shade it. We shade it. Okay, these 5, then we draw the corresponding comparison. 5, 1 comparison. These 3 and 7, we need a 2 comparison. 4 and 6, this level 3 comparison, right? Yeah. Now we can write the average formula. A, V, G equals 1 times 1, right? Yeah. Because 1 comparison node, only 1. 2 comparison node, there are 2, 2 times 2. 3 comparison node, there are 2, also 3 times 2. Over total 5. We have 5 nodes. That's your answer. Okay. You're doing this way. Okay? This way. So the binary tree. But that's how we calculate the average. Yeah. So let me see how many minutes do I have. Yeah. I have, about 5 minutes. Any more question? The Zoom side student, any question from the Zoom side? If no question, I will let you go. Okay. Nine? Yeah. No, number 9. All right. Let's see. Let's see if we. Number 9. In order to avoid worst case situation, which of the following sorts should, based on the basic property. Yeah, here I cannot tell you anyone, but if you recall which algorithm we consider to avoid the worst case, right? You go to the introduction part. There is one we want to avoid worst case. Yes, just covered in the notes. It's not hard. Basic property. Yep. Basic property. Yeah. All right. Yeah, I feel you should be okay. Yeah. Yeah.
Yeah.
Hopefully.